Number 2, if the sprinter from the previous problem accelerates at that rate for 20 meters and then maintains that velocity for the remainder of the 100-meter dash, what will be his time for the race? All right, so to recall the last problem, number 1, the sprinter had an acceleration of 4.2 meters per second. And remember, that's squared. Let's not forget that. And he's going to accelerate at that rate for 20 meters. And in which case then he will attain a certain velocity at this point, right? So his velocity here could be considered the final velocity. If I consider, right, this frame of the problem as my first frame, okay? So if this is the final point here, then I must be referring to this as the initial point. All right, and then he's going to maintain his velocity, whatever final velocity he reaches for the first frame of the problem throughout the remainder of the problem, okay? And just a quick thing, right, if the total distance of the 100-meter race is 100 meters and he maintains that acceleration for 20 meters, then that means that the remaining, right, displacement here in which he has a constant velocity is 80 meters. All right, so first let's start trying to figure out some times and some times and velocities in this particular part of the problem. All right, so the initial velocity, I'm going to assume here that he is starting at 0 meters per second. He's accelerating at a rate of 4.20 meters per second squared. He's traveling for a distance, right, of 20 meters. 20 meters. We don't know the final velocity. All right, and we also don't know the time. So we're probably going to have to solve for both of these, okay? So first, it doesn't matter which one we choose here. Why don't we solve for the final velocity first? So pick a formula on the upper right-hand side that relates these four variables, and we find that it's going to be equation number 4. So the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration multiplied by the displacement. So the final velocity is what we're looking for. The initial is 0, the acceleration at 4.20, and the displacement was 20. So let's just plug that into the calculator. So we have 2 times 4.2 times 20 is 168, and then simply take the square root of that. Right, just plug that into the calculator, no big deal, and it becomes, again, considering significant figures, this is 13.0. Right, and that's in meters per second. Now, the final, and this is important, all right? So now the final velocity at this location is 13.0 meters per second, all right? And remember, this is the velocity at this particular point is only the final velocity if I'm considering this part of the problem as my frame. But now, when I now change frames and I want to consider this part of the problem as my next part, right? This final velocity turns into now be the initial velocity, all right? Meaning that it is now the initial velocity of this frame over here, and therefore the velocity at the end would be considered my final, okay? So we actually know this velocity, right? We just calculated it, so I'm going to get rid of that question mark, and we can plug in now 13.0 meters per second, as well as then that initial velocity will be 13.0 meters per second. So that's great. All right, so we got that out of the way. Now, why don't we go back and solve for the time, okay, for this first frame of the problem. All right, so how do we want to do this? I mean, we could do this, let's use equation number 2, right? We could choose other equations, but I'd rather not use an equation that involves the final velocity because maybe I made a mistake. I don't want that mistake to propagate into the next part of the problem. So let's do change in x is equal to the initial velocity times time plus 1/2 at squared. So the displacement was 20, the initial velocity was 0, so that whole thing just goes to 0, plus 1/2 of the acceleration, which is 4.20, multiplied by time squared. So let's clean it up a bit. So we have half of this should be 2.10, right, t squared. Then just divide out the 2.10, 2.10. So now we're left with t squared being 20 divided by 2.1, so 9.52. So we get 9.52. And remember to solve, we got to take the square root. Okay, so the time, remember when you take the square root, you always get a positive and negative answer. However, we're only going to consider the positive value here because we're talking about time. All right, so square root of 9.52 and 3.0 9. So we get 3.09 seconds. So that's the time, I'll call it, for the first part. Okay, that's the time for the first part. So we found this out. All right, so the time since we're looking for time overall, I'm going to write that over here. So time for the first part here in the first frame was 3.09 seconds. All right, great. Now why don't we solve for time that it took to go from now this point in which he reached a velocity of 13 meters per second, and now he's going to travel at a constant velocity, the problem said, until he reaches the finish line. Okay, so the initial velocity here is constant, so that means the initial would be the same as the final over here, and it also means that it's the same as the average, right? So I can really just make this second part simple. In talking about the second frame of the problem, right, from here to here, we're going to be dealing with just the average velocity formula, is displacement over time. So his average velocity for the whole period was 13.0. He has to travel then in that second frame 80 meters. So how long is it going to take? So simply just do a cross multiplication. 80 divided by 13, we get a value of 6.15. So there's going to be 6.15, and that's in seconds. That's for the second frame of the problem, right? So let's put that here. So T2 would have been 6.15. And now how do we solve for the total time? Yeah, right? We just take time 1 here and time 2, right? Add them together, okay? So we get 3.09 plus 6.15. And we get 9.24. So we get 9.24 seconds total time. Guys, thanks for checking out the video. I hope this helped. Please remember to subscribe, and I will see you in the next lesson.